Point anomalies are easy. The costly failures are often unusual shapes spread across a window. STUMPY's matrix profile surfaces those rare subsequences as discords without labeled anomalies. You'll learn the shape of a workflow that scans a series, compares windows, and returns the rarest shape. I'm Professor Pi, teaching AI foundations with simple Python. Time series problems often fail because a single spike doesn't tell the whole story. Operations teams care about stretches of behavior, a waveform that drifts for a minute, not just one bad reading. Matrix profile anomaly detection with STUMPY handles that by comparing short windows to each other and flagging the windows that have no good match. People use it when labeled anomalies are rare or impossible to collect, and when shape matters more than an isolated value. It scales from small signals to streams with millions of samples and is fast enough for exploration on one machine. At the core, slide a fixed-length window across the series, and for each window, ask how similar it is to every other non-overlapping window. If a window's closest match is still quite different, that window is suspicious. Normal behavior shows up as repeated patterns. Anomalies are shapes that don't repeat. That makes the method good for finding motifs and discords, but it depends on a sensible window length and C normalization, so amplitude and offset don't drown out shape. We will build a compact pipeline that creates a synthetic series with one unusual local shape, computes the matrix profile with STUMPY, ranks windows by how unmatched they are, and then flags suspicious ranges with a simple threshold. You will be able to point to a specific time range and show why it looks unusual compared to the rest of the series. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. The first step is to create a controlled signal so we can see how window comparison works in practice. This snippet builds a small time series with one unusual local shape. Point-based detectors usually look at individual values, but matrix profile methods compare windows, so the first move is choosing a subsequence length with M. The repeated 0-1 rhythm gives STUMPY something normal to compare against, while the middle shape is visually different without needing labels. The windows count tells us how many candidate subsequences STUMPY.stump will score in the next step. The output shows the signal size and how many sliding windows are available for comparison. Now that we have a series and a chosen window length, we need a reliable way to compare every window to every other. This code computes STUMPY's exact matrix profile for every window in X. Instead of building handcrafted window features, STUMPY.stump compares each subsequence to its nearest non-trivial neighbor under Z-normalized distance. The MP object stores those nearest neighbor distances in mp.ps, and those values become the anomaly scores we use next. Low values mean a window has a close match somewhere else. High values mean the shape is harder to match. The output confirms that every candidate window received a finite score, so the ranking step has usable input. With a per-window score in hand, the next need is a simple ranking to find the most unusual subsequence. This snippet turns the STUMPY matrix profile into a discord detector. The key idea is simple. A discord is the subsequence whose nearest neighbor is still far away, so we sort MPP from largest to smallest. Top is the starting index of the rarest looking window, and score is its nearest neighbor distance. This is not a supervised classifier. There are no anomaly labels, loss curves, or learned thresholds yet. The output shows the highest ranked discord window and its score, giving us a concrete candidate to inspect. We can make the ranking interpretable by showing what the top discord was compared against. This example connects the score back to the original shape. STUMPY's MPI in stores the nearest neighbor start index for each window. So near tells us what the discord was compared against. Slicing X with top and near makes the result interpretable. We can see the unusual subsequence beside the closest normal-looking alternative. That matters because window anomalies are often hard to explain from a single timestamp. The output shows the selected discord shape and its nearest neighbor, which makes the ranking easier to trust. Finally, we want a small, actionable detector that produces ranges you can review or annotate. This code turns the STUMPY discord ranking into a small baseline detector. The threshold is deliberately simple. Windows with MPPI at least 2 standard deviations above the mean are flagged. Increasing this limit usually returns fewer, more extreme candidates. Decreasing it catches more windows, but can include more ordinary variation. SPANS converts window starts into inclusive time ranges, which is closer to how teams review incidents or create annotations. The output shows the flagged subsequence ranges and the numeric cutoff, completing a compact, unsupervised anomaly workflow. This toy example maps cleanly to a real project. Replace the synthetic series with a slow-moving sensor or CPU load trace. Choose M to match the expected anomaly duration, and the flagged spans become incident candidates for a runbook or human review. 3 quick points to remember. Matrix Profile with STUMPY finds rare subsequences by comparing windows, not individual timestamps. Use this when shape and repetition matter, and when labeled anomalies are scarce. One caveat: the subsequence length M determines the scale of anomalies you can detect, so pick it to match the event duration you care about. To move this example forward, tune the subsequence length M on a real dataset, such as a minute resolution server CPU trace or an ECG lead, and measure how the number and relevance of flagged spans change. That single parameter will usually give you the biggest practical improvement. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.